This video is about deriving the formula for maximum deflection of a simply supported prismatic beam loaded with a point load or concentrated load at midspan using the moment area method. Solving this problem using the moment area method can be carried out using simple steps, which begins with constructing the deflected shape or elastic curve. Then we will analyze the geometry of the elastic curve and tangents drawn on the curve and find relationship which is equivalent to the theorems of moment area method that in return can be converted to equations that will solve the problem, like we have done to cantilever beams and simple beam under the action of uniform load. I have provided the link of these videos in the description below. Here is now our beam and the elastic curve of our beam. Symmetrically loaded simply supported beams bends or deform under loads identical to each other. Identical because maximum deflection is always located at midspan. But of course, the degree of the equation of the curve are not identical to each other, like we can see in the figure. We will now begin to draw the tangents on the curve, like for example at point 1, the slope of the line is theta 1, and if we will draw the tangent at point 2, the slope is theta 2. However, if we will draw the tangent at point C, the slope of the tangent line theta c is equal to 0. The lowest point of the curve is the location of maximum deflection at point C. Since point C is the lowest point, the tangent line at this point is a horizontal line or a line that has zero slope, or theta is equal to 0. Remember that tangent lines are drawn just to touch the curve at that point. This situation will give us a very important hint in solving the problem, because it is very clear from the figure that the maximum deflection is equal to deviation of point A with respect to a tangent which is drawn at C. The second theorem of moment area method directly defines the equation that will solve this vertical distance. It can be obtained equal to the product of area and distance. Area being defined as the area of the bending moment diagram between A and C, divided by deflection rigidity EI. Distance is being identified to be the distance measured from the centroid of area under consideration up to the point where deviation is computed. We will now draw the bending moment diagram. To visualize the area and the distance being considered, we will compute for the reaction which is P over 2 at its support. Since the beam is symmetrically loaded, then we will draw the shear diagram. The area of shear diagram, which is in the form of a rectangular shape with dimension P over 2 and L over 2, will be the maximum ordinate of our bending moment diagram. The resulting area of the shear diagram is equal to PL all over 4. Here is now the bending moment diagram of our beam over its entire length. In our working equation, we need only the area between A and C. Therefore, we will only consider half of the area of the bending moment diagram over its entire length, which is equivalent to the area of bending moment diagram that we can see in the figure. It is vital for us to have a clear understanding about the difference between the point where the tangent is being drawn and the point where deviation is being computed to identify correctly the distance which is to be multiplied to the area. In this situation, tangent is drawn at C, deviation is computed at point A. Therefore, the distance should be measured from the center of the area to point A, not from the center to point C. These distances are vastly different from each other, which will lead to mistake if we do not pay proper attention. To avoid mistake, it is usual to write first the point where deviation is being considered, which is point A in this example, the tangent symbol, and the point where the tangent is drawn, point C in this example. So we will have our guide for what our reference is when measuring the distance. Since the first letter we have written is the point where deviation is computed, this point will also be our reference point to determine the distance we will multiply to area in computing deviations. We will now solve for the area of the bending moment diagram between A and C, which is a triangular area. Therefore, it is 1/2 of its base multiplied by its height, and it is equal to PL squared all over 16. And the distance, which is equal to 2/3 of L over 2, since our area is a triangular area, so we can derive it equal to L over 3. If we will now substitute area and distance in the equation, The formula for the maximum deflection of simply supported prismatic beam loaded with a point load or concentrated load at midspan is PL cubed all over 48 AI.